Hey everybody, Mr. Judson here. Of all the stuff we do in Chapter 8, this is probably the easiest one that we look at. What we're going to do is we're going to say if we have integrals that have sine raised to some exponent times cosine raised to some exponent, dx, then what we want to do is we want to look at that exponent, and if n is odd, we want to factor out one sine and convert the rest to cosines. When we say convert the rest to cosines, I mean using the Pythagorean identity. Sine squared plus cosine squared equals 1. That's what we'll use to convert the rest. So like if this was an exponent of 3, I would factor one sine out. I'd have a sine squared of x left. Now when I say factor it out, I don't mean to the outside. I mean just put it in front here. And then I would use this to convert the rest to cosines. Okay. If m is odd, so my cosine is raised to an odd exponent, same thing. Factor one cosine out and convert the rest to sines, using that same Pythagorean identity. If they're both odd, then just pick one. Pick whichever one you think is going to be the easiest. Okay? So let's do an example here. All right, so here's an odd exponent. And so what I want to do is I want to factor one of those signs out. So I would say the integral of the sine of x times sine squared of x times a cosine squared of x dx. And I want to convert this over to cosines. So we know that sine squared plus cosine squared equals 1. Therefore, a sine squared will equal 1 minus cosine squared. And so I want to put that in place of this thing. So now what I have is sine of x times 1 minus cosine squared of x times another cosine squared of x dx. And so now what I'm going to do is I'm going to go ahead and distribute this sine to both of these, and I'm also going to distribute this cosine squared to both of those. So what I'm really going to do is say sine cosine squared times each of these. And so what I get is the integral of a sine of x cosine squared of x. That's what I get when I multiply it times 1. And also separate this into two separate integrals at the same time. So go ahead and call that dx, and then minus the integral of sine cosine squared times this would be a sine of x cosine to the fourth of x dx. And so now what we want to do is we want to look at this and think of this as something inside parentheses raised to an exponent. Same thing over here. And so this really just becomes a substitution. So if I say let's let u equal a cosine of x, then du is going to be negative sine of x times the derivative of the angle, which is 1, and I just took the derivative of x. So let's see, in order to see that negative sign, I'll just bring this negative sign in front or back into the integral. I'll bring this back into the integral, and here I'll need to put a negative sign there and then another one out in front. So now what I have is u squared, negative sine of x dx, that's du. Still have that negative sign there. And then here, plus the integral of u to the fourth, negative sine of x dx, that's du. And so what I get is a negative u to the third over 3 plus u to the fifth over 5 plus c. And so now if I just get my cosine x back in there, I'll start with the larger exponent. I've got cosine to the fifth of x over 5 minus cosine cubed of x over 3 plus c. So whichever exponent is odd, we'll factor out one of those, change whatever's left over to the other trig function, and then it just becomes, a substitution problem. We'll have to divide this into separate integrals, but we'll do substitution to finish that off. Let's try another one. All right, you guys go ahead and give this one a try. All right, so here's my odd exponent. So I'm going to factor one of those out. So I've got the integral of a sine to the fourth of 2x times cosine squared of 2x times another cosine of 2x and then dx. And so I want to convert these over to sines. So again, sine squared plus cosine squared equals 1. So therefore a cosine squared would equal 1 minus sine squared. So I now have sine to the fourth of 2x times 1 minus sine squared of 2x times a cosine of 2x dx. So I'll distribute both of these to each of those terms. So what I'm going to get now is a sine to the fourth of 2x times cosine 2x. I took both of these times 1, so I just get those two things. dx, I'm also going to separate this into two separate integrals. And my next one, I've got sine to the sixth of 2x times a cosine of 2x. Right, so now we're just going to think of these as something inside parentheses raised to an exponent, right? Because we should be writing it this way. Sine of 2x and then to the fourth, right? All right, so we're going to let, I guess I'll write it right here. We're going to let u equal sine of 2x. So du is going to be, derivative of that would be a cosine of 2x times the derivative of the angle, which would be 2, and I just took the derivative of x. So I need to see a 2 here and here to be able to substitute du in place of cosine 2x times 2 dx. So that means I need to put a 1/2 out in front of both of those. Alright, so now what I have is 1/2 the integral of u to the fourth. All this is my du minus 1/2 times the integral of u to the sixth power du. And so now what I get is u to the fifth over 5 times 1/2 minus 1/2 times u to the seventh over 7 plus c. And so now I could go ahead and put the sine of 2x back in here. So I've got sine to the fifth of 2x over 10 minus sine to the seventh of 2x over 14 plus c. Alright, so that's not too bad. Yeah, so you might want to take a second to write these two rules down. Alright, so here's our next rule. What if we have an integral with tangents and secants? And those are the only two things we're looking at. What if we've got sines and cosines? What if we've got tangents and secants? So if m is even, this exponent right here, that means we want to factor out a secant squared and convert the rest to tangents. The reason we're factoring out a secant squared is because that's the derivative of a tangent. So if I can get everything else in terms of tangents, here's its derivative, then I can do a substitution. Okay? And if n is odd, so that's this one, factor out a secant and a tangent. So get one of each of these, factor it out, and then whatever's left here, change that to secants. If n happens to be 1 and you factor 1 out, there's nothing left to change, right? So we just wouldn't have any additional secants in there. Okay, but that's the whole goal of the two things we're doing today, is to try and create the derivative of one of these functions so we can do substitution. All right, go ahead and take a second to write these two rules down. All right, so let's go ahead and try this one. So this one's an even exponent, so that means I can factor a secant squared out because that's the derivative of a tangent. So let me rewrite it this way. I've got secant squared of 3x times a tangent of 3x, and the secant squared that I cancel out, or that I factor out, I'm going to write over here. Because that's going to be my du. Alright, so now I need to change this over to tangents. I know that a tangent squared plus 1 is equal to a secant squared. So what I have now is the integral of a tangent squared of 3x plus 1 times a tangent of 3x and then a secant squared of 3x dx. And so now I'll distribute all of this to each of these terms. So what I'm going to get is the integral of a tangent cubed of 3x times a secant squared dx, and then plus, when I take both of those and distribute to this, I get a tangent of 3x times a secant squared of 3x dx. Alright, so now we'll do our substitution. I'm going to let u equal a tangent of 3x. Therefore, du is going to equal a secant squared of 3x times the derivative of the angle, which is 3, and I just took the derivative of x. So I need a 3 here and here, which means I need 1/3 out in front. Alright, so now I'll put a u in place of this, so I've got 1/3 the integral of u cubed secant squared of 3x times 3 times dx, that's my du, plus 1/3 the integral of u du, and so what I get is 1/3 times u to the 4th over 4 plus 1/3 times u squared over 2 plus c. And then my final answer here will be a tangent to the 4th of 3x over 12 plus tangent squared of 3x over 6 plus c. So the only thing that I could think of that might trip us up a little bit here is somebody maybe looked at this and said, well, that exponent's odd, I'm going to factor out a secant and a tangent. Then when I do my substitution, I'll just have u to the 3rd that secant times tangent would become my du. So you could have gone a different route and got an answer that's different than this, and it would be equally correct. Okay, it would not be wrong. So once in a while, you might go one way, but maybe the book goes a different way, so you go and check your answer in the back of the book, and it looks different, and you feel like you made a mistake, but you could have done everything exactly right. All right, let's try another one. This time I've got the integral of tangent to the 6th of x dx. You guys go ahead and try it. So there are no secants. We were told if this was odd, to factor out a secant and a tangent. It doesn't look like either option is going to work. So I think what I would do is I would probably call this integral of a tangent to the 4th of x times a tangent squared of x dx. And then I would go ahead and change this using a Pythagorean identity. And we'll see what happens. So again, we know tangent squared plus 1 equals a secant squared. So tangent squared would equal secant squared minus 1. And so if I did that, I would have tangent to the 4th of x times a secant squared of x minus 1 dx. And so if I distribute this, I've got the integral of a tangent to the 4th of x times a secant squared of x dx minus the integral of a tangent to the 4th of x dx. So the derivative of a tangent is a secant squared, so I do think I can do this integral. Not so sure about that one. I may have to do the same thing again. So I know that if I do substitution here, I'm going to let u equal tangent of x. So du is going to be a secant squared of x times the derivative of the angle, which is 1, and I just took the derivative of x. So I think this one we're okay with. I've got u to the 4th du minus, so I guess I'll just do the same thing again. I'll think of this as a tangent squared times a tangent squared. So I've got the integral of tangent squared of x times, we're going to put this in place of the other tangent squared, right? If this is tangent squared times tangent squared, there's the first one. The second one we're going to convert. Secant squared of x minus 1 dx. Alright, so this will become u to the 5th over 5 minus, now I got to be careful here, I have to subtract everything that this becomes. So let's just put brackets there. I've got an integral of tangent squared of x times secant squared of x dx. When I distribute that to here, I'll have minus the integral of a tangent squared of x dx. And so again, we're going to let u equal tangent of x. So I'll go ahead and change this back now. This becomes tangent to the 5th of x over 5. This is going to be minus the integral of u squared, secant squared of x dx, that's our du. Negative times a negative makes that a positive integral. And I can't do the integral of a tangent squared. So I'm going to have to put this in place of there one more time. So secant squared of x minus 1. I think we're almost done with this one. So here I've got tangent to the 5th of x over 5. This will be u cubed over 3. I'm just going to go ahead and put the tangent back in there right now. So tangent cubed of x over 3. The integral of a secant squared of x is just a tangent of x, and the integral of 1 is just x plus c. So we had to, whoops. There we go. So we had to do a conversion with the Pythagorean theorem, what, once, twice, 3 different times on this one. All right, let's try one more problem. All right, let's give this one a shot. All right, so again, a little confusing. We've got a square root here, and if, let's see, if I can't factor out a secant squared, so I'm not going to be able to get the derivative of this. So what I need to do is I need to try and get the derivative of a secant, right? Derivative of secant is secant x times tangent x. So in order to make that happen, I'm going to have to do something a little bit different. I'm going to multiply top and bottom here by a secant of x. So secant x over secant x, that equals 1, so I haven't changed anything. And what I want to do is I want to factor out a secant x and a tangent x. So I'm just going to write those over here. Secant x, tangent x, dx. And what I'm left with here is a tangent squared. And then this secant times the square root of a secant, add the exponents, you get 1 plus a half. That's secant to the 3/2 of x. And what I want to do is I want to convert what's left to secants up here. All right, so again, we know that a tangent squared plus 1 is equal to a secant squared. So a tangent squared is equal to secant squared minus 1. So I've got the integral of secant squared of x minus 1 over secant to the 3/2 of x times all this. And now what I'm going to do is I'm going to divide this into 2 different fractions. So what I have is the integral of secant squared over secant to the 3/2. So you just want to subtract the exponents. 2 minus 3/2 would be 1/2. So I've got secant of 1/2 x. And then I'm also going to do the same thing here. I'm going to do negative 1 over this. And that would be a negative secant to the negative 3/2 of x. And then this secant x, this tangent x, and then dx. So see, what we're doing is, if we let u equal this, then the derivative of secant is secant x tangent x. So I can do my substitution now. I'm not going to write 2 separate integrals. I'm just going to say, let's let u equal a secant of x. Therefore du equals secant x tangent x. And I just took the derivative of x. And so that means I've got the integral of u to the 1/2 minus u to the negative 3/2 du. So now we just got to add 1 to the exponent and divide by the new exponent. So u to the 3/2 over 3/2, which means I'll multiply by 2/3, minus u to the, this is a negative 3/2, so if I add 1 to that, I get a negative 1/2. So I'll divide by a negative 1/2, which means I'll flip it over and multiply by a negative 2 over 1, and then plus c. And so my final answer here is 2/3 secant, I'm just going to write it this way, to the 3/2 plus 2 times, let's see, that's a negative exponent, so we got to drop that below the fraction bar. So that would be 2 over the square root of a secant of x plus c. So we'll have a couple problems that'll make us think a little bit like this one and the last one, but I think you'll find that most of them are pretty straightforward. Alright, so here's our assignment for today. Number C14, we're going to do page 540, 5 through 9, 12, 27, and then 33 to 36. Alright, you guys, there it is. Got our first 3-day weekend. We'll do the same thing next week. And so, you guys have a good day, enjoy the weekend, and stay safe. We'll talk to you later. Bye.